18 सेशन है ये?
Yes, sir.
Very good. So at the moment, 12 students have joined. Let me share my screen. I have put the link on WhatsApp also. और क्या है? Let me start the recording also. Okay. Last time we studied rainfall measurement using
Radar, sir.
radar and satellites.
Satellite.
Hopefully you have seen the video also, which I asked you to see about what was the mission the video was talking about. Mission क्या था? So who and who are with me? Roll number 92. 2018 92. How are you?
Alhamdulillah, sir, fine.
Please enhance your voice. It is too low. या तुम्हारा mic बहुत दूर है.
Yes, sir.
Enhance your mic. What we call loudness, or increase your voice.
Sir, increase ही है.
हाँ बेहतर है और ऊंचा बोलो. So last time we studied satellites and what else? Radar, and a video was shown. That video was about what project? Roll number 92. Yes sir, no sir की जगह नहीं है अभी. I asked you a question. Last time a video was shown about satellites and it was talking about a project. What was that one? What was the name of the project? What is your name? 92 आपका नाम क्या है? नाराज हो गया लगता है. Then if I skip 2, 3. Akib Ali. आकिब अली क्या क्या हाल है आपके?
Yes, sir.
How are you?
I'm fine, sir. How are you?
Alhamdulillah. So tell me what was the video about? Last time we saw a video about satellites. This video was talking about which project?
Sir, actually, I was quite busy last week.
Last week you were busy, but you attended the lecture.
Yes.
Everybody is very busy, na? Except for studying. Everybody is very busy.
Yes,
So
sir.
don't tell me you are busy.
Yes, sir.
And don't tell me you people are busy. You are busy in studying, I know. So I am saying no response. You are busy.
Yes, sir.
Very good. Or I skipped 2 more. Hamza Niaz. Hamza, क्या हाल है आपके? अल्लाह का शुक्र है, very good. So same question to you. What was the video talking about? PM क्या? GPM, global press. There's a there's a constellation of 9 satellites which are capable of measuring the rainfall. They were talking about 3 special bands on board on GPM. किसी एक का नाम बता दो. They were talking about 3 special band. एक core band था. So they can analyze the clouds like an X-ray machine, like a ultrasound. Okay. So thank you, Hamza. You told me that it was GPM Global Precipitation Mission, and it is not a mission of one country. Few countries, including India, Japan, USA, are part of this mission, and they are measuring the rainfall. They are seeing the cloud, and from there they can estimate the rainfall all around the globe. Thank you, Hamza. Mic off कर दो. जवाद अहमद,
यस सर.
आपके क्या हाल है? खैरियत है?
जी अल्हम्दुलिल्लाह.
Okay, Jawad, can you tell me what is the working principle of radars? भाग गया. Mubin,
Yes, sir.
same question to you.
सर एक्सक्यूज मी, ये
Sir,
किसी ने रिमूव कर
जो
दिए.
किसी ने क्या किया है? जवाद, किसी ने क्या किया है?
रिमूव कर दिया सर ग्रुप से 2 दफा. अब
अच्छा, आज रिमूव हो रहा है. ओके. जो उस बच्चे को पकड़वाएगा जो रिमूव करता है उसके लिए इनाम है, या खुद ही हो जाता होगा यार. कुछ सारे शरीफ बंदे हैं, मुझे पता है. ओके. अगर किसी और को प्रॉब्लम हो रहा है रिमूवल का तो मुझे बता दे, देन आई इसको रीसेट करता हूँ. ओके मुबीन, आंसर में अब तो रिमूव नहीं होना.
सर डॉपलर इफेक्ट.
मुबीन जवाब दे रहे हैं.
यस सर.
ओके, व्हाट वाज द क्वेश्चन?
सर वो हाउ रेडार वर्क.
ओके, सो नाउ टेल मी
वर्किंग
हाउ.
प्रिंसिपल.
अगर आपने अपने छोटे भाई को बताना हो कि रडार कैसे काम करता है तो आप कहोगे डॉपलर इफेक्ट.
नो सर, वो
समझाओ ना जरा.
इलेक्ट्रोमैग्नेटिक. सर वो इलेक्ट्रोमैग्नेटिक वेव की बीम जो है वो ट्रांसमिट करते हैं रेडार, और जो है वो एंटीना की डायरेक्शन में सर. और जो ये रेडार जो वेव्स रेडिएट होती हैं वो स्पीड ऑफ लाइट की स्पीड में ट्रैवल करती हैं. और
सही.
सर ये वेव पार्शियली रिफ्रैक्ट होती हैं. वो जो प्रेसिपिटेशन पार्टिकल जहाँ पे हो वहाँ पर उससे पार्शियली रिफ्लेक्ट करके तो रिडार में दोबारा रिफ्लेक्ट होती हैं वापस, और एंटीना में रिसीव होती हैं. तो एंड उसके बाद जो उसकी कुछ पार्ट उसका जो डायफ्रैक्ट स्कैटर्ड और एब्जॉर्ब हो जाता है.
सही है. तो received back by the receiver, then
और सर वो सर कुछ पार्ट उनका डायफ्रैक्ट हो जाता.
हो गया ना, कुछ पार्ट वापस आ गया. देन
सर
छोटे
वो
भाई
जो
को
वो सर रिटर्न पावर होती है जो एनर्जी रेडार में वापस बैक आ जाती है टर्न टू द रेडार.
रिटर्न पावर इज मेजर्ड बाय द इलेक्ट्रॉनिक इंस्ट्रूमेंट. ठीक है. Then
सर फिर उसका टाइम इंटरवल जो है वो हम मेजर करते हैं जो
जी सुन रहा हूँ।
सर वो टारगेट जहाँ से वो जो है डिस्टेंस मेजर करते हैं हम वो टारगेट और रेडार के दरमियान।
Okay, we can find the distance or range between radar and the clouds or target using the time of the return beam. Noting the time of the return beam, we can estimate the range. Range estimate होगी. How we estimate the range? Okay. Good. मुबीन के बाद कौन है? मुइन. मुइन आगे कंटिन्यू करो. How we estimate the range?
Yes, सर वो जब हमारे पास जब हमारे पास एनर्जी लॉस में आती है तो उसको हम फिर उसकी ना क्या कहते हैं वेवलेंथ और उसकी सारी चीज़ें उसकी एम्पलीट्यूड और वेवलेंथ डायमीटर टू वेवलेंथ रेशियो लेते हैं। फिर उसके मुताबिक हम उसको फिर एन्यूटेशन और उसके अंदर एटेन्यूएशन को यूज़ करते हुए हम उसकी वेवलेंथ और डायमीटर रेशियो यूज़ करके फिर हम उसको बता सकते हैं कि ज़्यादा रेन हुई है या कम रेन हुई है। अगर डायमीटर टू वेवलेंथ रेशियो ज़्यादा होगी तो इसका मतलब ये हुआ है कि उसके अंदर लॉस ऑफ एनर्जी ज़्यादा होगा। फिर उसके मुताबिक उसमें हम ये बता सकते हैं कि ज़्यादा रेन हो सकी, क्योंकि ज़्यादा रेन होगी तो हमारे पास प्रेसिपिटेशन की वजह से डिफ्लेक्ट होगा, स्कैटर ज़्यादा होगी।
Higher the rain, higher the return power, or less the rain, higher the return power?
सर हायर द रेन लेस द रिटर्न पावर।
That's not true. If there is no cloud, it means there will be very high return power.
सर रेन की प्रेसिपिटेशंस की वजह से वो क्या कहते हैं स्कैटर्ड नहीं हो जाएगी?
Scatter हो जाएगी, reflect भी ज़्यादा होगी when there are more liquid or crystal particles, reflect ज़्यादा होगी as compared to if there is no obstruction in front of the beam. If there is no obstruction, if there is rain or clouds are there, then there will be more return power. So this you can find from the equation of return power की equation क्या थी? It was directly proportional to d power 6.
Yes sir, d की power 6 वो फिर a into r into power b coefficients.
Larger the particle size, more is the return. More number of particles mean more volume, d power 3, more is the return. ये तो quite simple सी बात थी कि आगे obstruction आ जाएगी तो reflection ज़्यादा होगी, scatter भी बढ़ जाएगा, लेकिन previously तो it was not returning back, previously it was going. Okay, so there was a term we call reflectivity.
Yes,
Z was a symbol for that. So how it is related with rain, and I am asking this with Mohsin Rana. Muin, thank you.
Thank you, sir.
Mohsin Rana. How the reflectivity was related with the rain, rate of the rainfall. Mohsin क्या हाल है? अब मोहसिन राना मौजूद है और माइक ऑन है। मोहसिन आपकी आवाज नहीं आ रही, अपना माइक चेंज करो। अभी कुछ आ रही आवाज। नो, अब बोलो।
सर जो रिटर्न पावर होती है ना वो रिफ्लेक्टिविटी को मेजर करती है, और जब वो हाइड्रोमीटर के साथ कनेक्टेड होती है, जो हाइड्रोमीटर वो जो रिफ्लेक्टिविटी ऑफ जो हाइड्रोमीटर की ग्रुप्स की होती है वो डिफरेंट फैक्टर्स पर मेजर होती है, जैसे वो ड्रॉप जो साइज की डिस्ट्रीब्यूशन होती है, पार्टिकल्स जो एक यूनिट वॉल्यूम में हो, या उसकी जो फिजिकल स्टेट होती है वो सॉलिड है या लिक्विड है, और उसके अलावा जो उनके एलिमेंट्स की शेप होती है उस पर डिपेंडेंट होती है।
ठीक है, we told you a relationship between reflectivity Z and rain rate. What we call that relationship?
सर उसको नाम तो नहीं पता, फॉर्मूला ये है
बता दो फार्मूला।
PR is equals to CZ और R square।
अब मैं रिफ्लेक्टिविटी की बात कर रहा हूँ, दैट इज दैट। मैं रिटर्न पावर की बात नहीं कर रहा। रिटर्न पावर इज अनदर पैरामीटर, रिफ्लेक्टिविटी इज अनदर पैरामीटर।
सर वो Z is equals to sigma D power 6 is equals to AR power B।
So when I asked you how Z is related to rainfall, तो कौन सा फार्मूला बताना चाहिए?
वो डायमीटर का।
इसमें रेनफॉल कौन सी है? डायमीटर इज रेनफॉल।
सर वो
पावर फंक्शन हमने किसको बोला था?
सर पावर B था और R power B।
AR power B. So this was power function. So rain is related with reflectivity through a power function. Function means a relationship. Function mean an equation. ठीक है?
जी सर।
So reflectivity is related with rain through a power function, and this A and B value we find through calibration of that station. Okay? Okay, good. Thank you, Masan. Let me reach to Umar Parvez. Umar Parvez.
Yes, sir.
Umar Parvez, can you tell me what is the wavelength which we use for meteorological radars? What is the suitable wavelength
Uh,
which we use
सर
for
वो CM जो होती है।
CM जो होती है? नहीं बेटे, आपको नहीं आ रहा, क्रॉस लगा रहा हूँ।
सर वो 5 से 10 होती है
5 से 10 वाट।
सेंटीमीटर।
हाँ, अब सही है। 5 to 10 centimeter is usually range of the wavelength which we use for. If lower the wavelength, then what will be the effect? Why not we use lower wavelength?
रिपीट करना, आपकी आवाज कट रही है।
I'm asking if we use a radar with a lower wavelength, smaller wavelength, what is problem with that?
सर वो अनसूटेबल हो जाएगी।
क्यों? मोहसिन अपना माइक ऑफ करो जी। क्यों
सर
अनसूटेबल?
वो उससे मेजर नहीं सही होगा ना, मतलब
वही तो पूछ रहा हूँ, क्यों नहीं होगा? Why smaller wavelength is not suitable for measurement of the meteorological parameter like rain? Why smaller wavelength is not suitable? अभी एक बच्चे ने बताया भी था।
सर
थोड़ी देर पहले।
मोटर
क्या कह रहे हो? जी जी बोलो बोलो, listening. Listening. 32 students are listening.
सर वो जो
कुछ बोल दो यार, क्या है, क्यों डरते हो? Okay, which friend you will call for your help?
सर किसी को भी बुला लें।
अच्छा चलो, तुम्हारा कोई दोस्त नहीं है, ठीक हो गया।
सारे दोस्त हैं, किसी को भी बुला लें।
Okay, do you know the effect of diameter to wavelength ratio? Umar Parvez?
Yes, sir.
What is the effect? If diameter to wavelength ratio is large, then what
सर
will
वो
be the...
अटेनुएशन होती है, वो ग्रेटर हो जाती है।
तो इसलिए तो कह रहा हूँ, जैसे जैसे वेवलेंथ स्मॉलर होती जाएगी, डाया टू वेवलेंथ रेशियो बढ़ती जाएगी। यहीं से जवाब आना था आपके उस सवाल का।
सही।
तो स्कैटर और अटेनुएशन मीन रिडक्शन ऑफ द पावर। तो अटेनुएशन enhances because scatter enhances. So we don't go for smaller wavelength radars. So 5 to 10 centimeter wavelength radar are considered good. Or sometimes we mention wavelength of the radar, sometimes we mention the frequency, because this frequency and the wavelength are related. C is equal to lambda f. तो दोनों में से एक बता दें. C is speed of light, तो lambda बता दें या f बता दें, दूसरा पैरामीटर हम कैलकुलेट कर लेते हैं. Okay, so that was a brief review of our previous lecture. So if you have any questions, you are welcome. कोई है तो बताओ. किसी के कोई suggestions हैं, कोई questions हैं? Welcome. No? Okay. Our today lecture is about another important metrological parameter which affect the hydrology of an area and which affect the water availability in a certain area, and that metrological parameter is evaporation. You are familiar with evaporation. It is the conversion of water from the liquid state to vapor state, and it depends upon the energy available at that place, the radiation which provides energy over there, so that controls the rate of evaporation. So evaporation we measure through the rate of evaporation. We usually measure net rate of vapor transport to the atmosphere is called evaporation rate. तो उसको हम evaporation rate कहते हैं, and we in metrology or in hydrology we consider it as reverse of the precipitation. Why we call it as reverse of precipitation? Because precipitation brings water from atmosphere to the ground, to the land, and evaporation takes the water from land towards atmosphere. So these are important components. If one of these components was not present, either evaporation or precipitation, the cyclic effect of water transport, the hydrological cycle would have not been continuous. So it is the water which comes to the land after passing through a number of phases. It evaporates at different places. So it controls the availability of water in a certain area, so its estimation is important. So in today's lecture, what we want to inform you, what are the factors which are controlling evaporation? एक चीज हम ये बताने की कोशिश करेंगे. Second thing is how evaporation is measured. What are different methods of estimation or measurement of evaporation? And one of the important instrument for measurement of evaporation is PAN-evapometer. So different kinds of PAN-evapometer are available, so their characteristics will be informed to you. And in the first part, different parameter which affect the evaporation rate from a certain surface, so that will be informed to you. The picture in the title slide was evaporation ponds made in USA for getting salt out of it. They make large plots or large ponds of water having a lot of minerals inside it, and when water evaporates, their minerals or salts are collected and they use it. So the cover page is actually the picture of evaporation ponds containing water and potash inside it. So they are getting out of these ponds the potash. Similarly, people can make the ponds for getting the salt out of the salty water. So that can be obtained from the evaporation ponds. In case of hydrology, evaporation reduces the water available in the reservoirs. For example, consider in your mind large reservoirs like Tarbela or Mangla Reservoir or Chashma Reservoir. So when water is standing over there, don't consider that its quantity will remain constant. Some water is seeped down into the ground. Some water goes up in the atmosphere through evaporation. Larger the area of the reservoir, more will be evaporation quantity. So we have to consider in mind that the large reservoirs are natural reservoir, natural lakes. They cause a huge quantity of loss of water through evaporation. Similarly, we lose water through evaporation from our agriculture fields also. When we apply water to the agriculture field, we have about 16 million hectares of land in Pakistan which is irrigated. So water evaporates from that land also, agriculture land saving. Similarly, the canals and water courses, all of these are conveying water from source towards the field. So on the way, because their top surface is exposed to environment, so evaporation is continuously occurring. So evaporation occurs from any surface which is exposed to atmosphere and which has availability of water, which has some moisture content inside it. So evaporation will start occurring over it. Evaporation, rate of evaporation and rate of condensation becomes equal when we reach to the vapor pressure over there. When vapor pressure reaches to its saturation limits, then rate of saturation and rate of evaporation becomes equal. Usually an amount of energy is required. An amount of energy is required to convert water into vapors. So that energy is transferred. This is a kind of transfer of energy also. This is a kind of transfer of mass also. Water transfer from liquid phase to the vapor phase. So we say there is a transfer of mass. Because energy is consumed in it, we say it is also transfer of energy also. So usually 600 calories of energy is required for transfer or evaporation of a gram of water. A gram of water. So for a kg, we need 600 kilocalories for a kg of water. So similarly, you know another value, latent heat of vaporization. So that energy which is required to vaporize a unit quantity of liquid into vapor phase. So that can also be used as a measure of energy required for evaporation or vaporization of liquid into the vapors. If the temperature of the water body is to be maintained, an equal amount of the radiation must be supplied from external source. So usually what happens is when evaporation occurs, the temperature of the liquid body reduces. Temperature of the surface from where evaporation is occurring, its temperature is reduced and we feel cooling effect. So if we want to maintain that temperature to its original value and we want that evaporation should occur, then some external energy equivalent to the 600 calories per gram of evaporation is required. So if we don't provide this energy, evaporation will occur and energy will be taken out of that water body, so its temperature will reduce. So that is a phenomena which takes place. Precipitation reaching surface of the earth goes back to the atmosphere through evaporation, and portion of this precipitation evaporates before reaching the surface. So evaporation is not always from the ground surface. In the topic of precipitation, we told you when vapors convert to the liquid phase, some of the smaller droplets, they don't reach to the ground and they go back to the atmosphere and they vaporize back. So not all of the condensed liquid droplets, small size liquid not all of them reach to the ground. Some go back to the atmosphere after evaporation and they are converted back. So some evaporation takes place in atmosphere, but we are much concerned about that evaporation which occurs from the ground surface, because we estimate the availability of water through the rain gauges. So if the rain gauge tell me that 10 millimeter of the rainfall have occurred, from there we will estimate so much water is available. So if we don't take into account the evaporation out of it, then we will be giving the wrong signal to the project managers. We have to tell them so much is the rainfall, so much is the rate of evaporation, so net water availability is so much. So evaporation has to be taken, evaporation occur in atmosphere, evaporation occur from the ground. For hydrologists, the evaporation from the ground is more important. Uh, Similarly, evaporation from the surface of the ocean, because two-thirds of the land is covered with water, and that is oceans. So evaporation from the ocean is of huge quantity. If you remember that hydrological cycle values, if 100 was the precipitation, 100 units were the precipitation on the land, how many units were the evaporation from the land, and how many units were evaporation from the oceans? Anybody remember that lecture? अगर 100 precipitation थी on the land, how much went to the atmosphere through evaporation from the land? किसी को याद
सर
है?
61 आई थिंक लैंड से थी और 400 समथिंग शायद ओशन से थी
424.
यस सर 424
424 far from ocean, and I think out of 100, 61, 38 मुझे याद आ रही है.
38 से ओशन से आ जाती थी और 61 लैंड से थी और 1%.
ठीक हो गया. So it means 61 was the unit of evaporation occurs from the land. 420. So evaporation from the ocean contributes huge water to the atmosphere through evaporation. Evaporation from the ocean contributes huge water. That is 5 times more. 424 divided by 61. That is about 7 times more. 7 times more evaporation occurs from the ocean, but it does not mean all of that comes to the land. Most of it fall back to the ocean in the form of precipitation on the oceans. If we are having a reservoir in a dry area like this one shown over here in the deserts of Nevada in USA, so over there, this estimation and the correct estimation of evaporation is quite important, because they are very short of water. They have a water stress area is there. So rate of evaporation need to be estimated very carefully in water stressed or water scarce environment. Over here, this white margin is showing you the margin of change of water level in this reservoir. When reservoir is full, reservoir reaches to the top of this level. When reservoir is empty, close to empty, it reaches over here. So at the moment, they are showing you a reservoir in the empty condition, and because water is very precious in the water stress environment, so every drop of water counts. So evaporation need to be estimated over there in a good manner, in an accurate manner. There are different factors which controls the evaporation, and we can categorize these factors into 3 groups. One related to the meteorological parameters, like temperature of that area, like wind speed of that area. So one group of factors are meteorological factors which affect the evaporation. The second group of the factor are related to the surface condition of the evaporating body, nature of the evaporating surface, and the third is the constituents within the water. For example, if salt are present within the water, what will be the effect on the so these 3 factors, group of factors will be described in the next slides. Factor affecting the evaporation can be grouped into 3 types: meteorological factor, factors related to the surface of evaporating body, and the surface and the factors related to the constituents, are the things which are mixed within the evaporating liquid. So here the meteorological factors are shown over here with the help of a figure. What factor will enhance the evaporation and what factor will reduce the evaporation. For example, if you go over there, it is the cloudiness or not cloudiness effect, whether it is full solar radiation are available or clouds are covering with the radiation. So if it is totally sunny day, no clouds are there, evaporation rate will be more. Reason for that is radiation available at the ground surface from where the evaporation will occur are more in sunny days as compared to in days with the cloudy with the cloud cover in a day. And meteorological people, they do estimate on daily basis the part of the sky which is covered with the clouds. So like they like they record how much is the rainfall, like they record how much is the wind speed. Similarly, they record the percentage of the total hemisphere, sky hemisphere or atmospheric hemisphere, the percentage or the part of that which is covered with the clouds. They go out, they divide the whole sky into quadrants, and they further divide them into half of them. So they divide it into 8 parts. So they call it octa. So they say that 1 out of 8 is covered with the cloud, 2 out of 8 parts is covered with the cloud, and they note this thing. So because this cloudiness do affect the amount of the radiation reaching to the ground, and that controls the evaporation. So one thing is sunny day or a cloudy day. Second thing they are showing over here is the temperature. High the temperature of the water bodies or high the temperature of the atmosphere, more will be evaporation. And if it is low temperature, less will be evaporation, because the rate of evaporation is dependent upon the energy available, and one of the measure of the energy available is the temperature of the body or temperature of the atmosphere. Temperature of the atmosphere controls temperature of the body. One factor which controls the temperature of the body is temperature of the atmosphere. It is not always that whatever is the temperature of the atmosphere, same is the temperature of the body. No, it is not. But after some times, if temperature of the atmosphere is more, then temperature of the body will also rise. So higher the temperature, if there are two water bodies, one with the higher temperature, one with the lower temperature, higher temperature body will be having more evaporation. Humidity is another factor, important factor, which controls the evaporation. Already informed to you, I think, if more humidity is there, if higher the humidity is there, low will be evaporation. Rate of absorption of water vapors by the atmosphere. The atmosphere which receives vapors from the liquid body, that rate reduces if its humidity of the atmosphere enhances, because close to the saturation level, no more vapor will be, when it reaches to the saturation level, no more water vapors will be reaching to the atmosphere, because rate of condensation and the rate of evaporation becomes equal. So more the humidity close to the saturation limit of the humidity, less will be the, so this is inversely proportional. Humidity and evaporation are inversely proportional. Similarly, wind speed. Wind causes circulation in the air, and that help in mixing the water vapors into air, and that help in taking the water vapors away from that area. So if there is a good wind blowing over there, if there is a high speed of the wind is blowing over there, mixing condition occurs, and also there is more acceptability of the vapors by the atmosphere, and more will be the evaporation. So higher the wind speed, higher will be the evaporation. What else? So these are the meteorological factors, 4 meteorological factors informed to you. One is sunshine, a sunny day or cloudy day. Second thing is temperature. Third thing is humidity, and the fourth is the water wind speed and the humidity, water vapors or humidity. So these factors affect. 3 of them are directly related to the evaporation, radiation, wind speed, and temperature, while water pressure, vapor pressure, or the humidity. Humidity can be measured in percentage of the humidity units. Humidity can be expressed in terms of vapor pressure of that area. So in any one way, we can express the humidity in terms of vapor pressure or in terms of humidity. So the other group of factors, which is the type of the surface which affect. So we can have different kind of surfaces available from where the evaporation do occur. Most of the time, either it is a water body from where the evaporation is occurring, or it is a soil surface from where the evaporation is occurring, most of the evaporation, or it can be a snowy surface from where the water vapor is uh, evaporation is occurring. How do it these surfaces are compared with the simple water body is explained over here. As far as the soil is concerned, the rate of evaporation is nearly similar to the rate of evaporation from the water body. So if there is a water body and if there is a soil with saturated soil, if it is there, if it don't have any lack of water, it is fully saturated and water is available at the surface, then we say that rate of evaporation is more or less similar to that rate of evaporation which can occur from a water body. So that is what is explained over here. Rate of evaporation from a saturated soil. Saturated soil mean it has abundance of water. It don't have lack of water. So two things can control evaporation. One is availability of water for evaporation, and another thing is availability of energy for evaporation. So if any of these two things are not available, then evaporation rate will reduce. So if we say there is a saturated soil surface, then rate of evaporation will be same as, more or less same as that of the evaporation from the water surface. And as the soil start drying with the passage of time, then its rate of evaporation decreases, and that decrease of evaporation enhances its temperature also. When rate of evaporation, when the soil reduces its moisture content and it dries out, then it's in the beginning its evaporation reduces, but along with the reduced evaporation, temperature of the soil enhances that, increases its evaporation again. So eventually evaporation, and if the dryness continues, if the moisture content reduction is continuous, we don't have any source of water coming to the soil, so this dryness will continue, and eventually evaporation will cease. Eventually the evaporation will stop, because if soil don't have more water available to it, evaporation will not be possible from there, if there is no water available near the surface for evaporation. It means evaporation from the land surface is bound by availability of amount of water over there. So if it is saturated, for example, we have just irrigated the land and the soil has become saturated, or for example, if there is just precipitation have occurred over there and soil is fully soaked or fully saturated. So in the beginning, evaporation will be more. Evaporation will be same as evaporation rate from a water body. So as soon as the dryness occurs in the soil, evaporation rate will start slowing down, and finally it will cease or it will stop. From the snow surface, although otherwise we expect that it should be more, because it is snow is a kind of water in solid state, but from the snow surface evaporation is very less. Evaporation rate from the snow surface is very less, and it is considered that maximum rate of evaporation from the snow is only about 1/4 of the evaporation from the water surface. So water surface से जो evaporation rate हो रही है, for example, if it is 4 millimeter in a day, so from a snowy surface, it will be maximum will be about 25% of that, about 1 millimeter will occur over there. What is the reason for that? Reason is explained in the earlier paragraph. Because evaporation is dependent upon the vapor pressure above that surface. Evaporation dependent on the vapor pressure above the surface, and the vapor pressure is a measure of the humidity at that surface. So if the vapor pressure on the surface is close to the saturation vapor pressure, then rate of evaporation and rate of condensation will be same. If vapor pressure at the top of the surface is close to the saturation vapor pressure, then it will be the same evaporation and condensation, and net result will be there is no evaporation. So it is said that the vapor pressure on the surface of air film over the melting ice is 6 millibar, and this is the maximum possible air to snow vapor pressure difference. So because vapor pressure deficit is very small over there above the snow surface, and the reason for that small deficit is low temperature existing over there. You have seen the saturation vapor pressure line in the lab also. As the temperature is low, saturation vapor pressure is low. So when temperature is low over there, so whatever the vapor pressure is present, that is close to the saturation vapor pressure. So it is reducing the rate of evaporation from that snow surface. Reasonable assumption informed us that 5 millimeter equivalent per day is the rate of evaporation from the snowy surface. 5 millimeter water equivalent in a day is the rate of evaporation from the snow surface. So the message from here is that snowy surface reduce the evaporation rate as compared to the evaporation from the normal water surface body like reservoirs or like ponds. As compared to that, it is about 1/4. Effect of the quality of the water. Now we are going into the third group of क्या कहते हैं क्या कहते third group of factors which affect, and we are talking now about the constituents of the water. So main constituent of we measure them as a concentration of the salts in the water. So it has been seen that the seawater, which has a huge quantity of salt inside it, if you remember the category of our waters in the river, we told you three categories. One was we call fresh water, one we call was marginal water, one we called was saline water, and we told you that if dissolved salts are less than 1,000 parts per millimeter, 1,000 parts per million ppm. If the dissolved salts are less than 1,000 parts per million, we say this is a kind of fresh water. And 1,000 to 2,000, we said it was marginal. 1,000 to 3,000, I think we said marginal water, and more than 3,000 parts per million, we said it is saline water in rivers or in groundwater. But in sea, if you see the value here, usually the salts are more than 30,000 parts per million, 35,000 parts per million are the dissolved salts. So it has been seen that if even the salts are of so much huge quantity, even then the rate of reduction is much. Only about 2%. Vapor pressure of the seawater is about 2% less than that of the pure water. The vapor pressure above the surface reduces only 2%. It is not the evaporation rate. The vapor pressure above the sea surface, because of the salt present in the water, reduces only 2%. The reduction in evaporation is less than that, or the evaporation reduction that is even less than that, indicated by change in vapor pressure. As with reduced evaporation, there is an increase in temperature of the water. So there is not much effect on the evaporation rate of the saline water bodies. Of the salt containing water body, there is not much effect, even if the salt is as high as 35,000 parts per million. The rate of reduction of evaporation is not much. Because so it is a little bit, but that enhances the temperature of that water body, that increases the evaporation. So the net result is for seawater, the reduction in evaporation is never more than few percentage over an extended period. So salinity has negligible effect on the evaporation. So, but if there is some foreign body available in the water, for example, if some oil has been spread on the surface of the water, then rate of evaporation reduces to much extent depending upon the rate of evaporation of that body. Any foreign material which tends to seal the water surface or will change its vapor pressure or its albedo. Albedo is the reflectance coefficient. if energy is incident on a surface, if energy is coming on a surface, then some energy is reflected back. So rate of the ratio of the reflected energy divided by the incident energy or coming energy, so that is called as albedo. Albedo is a coefficient which tells us how much is the reflection of the surface with respect to the energies. If 1 unit of energy is coming on a surface and half unit of energy is going back from that surface through reflection, then we say this surface has albedo of 50% or 0.5. So depending upon the albedo coefficient, the energy absorbed by the body is dependent. That surface which has more albedo, it means most of its energy is reflected back, means it is not receiving much energy, it is not absorbing much energy, means its temperature will not rise much, means it will not have much evaporation power. So albedo is a measure of reflection from a surface, and if a surface has high albedo, then it will have less energy absorbed, so its evaporation rate will be less. So different surfaces have different albedo. Those surfaces which seems to be white to us, they have more albedo. For example, freshly falling snow has very whitish color. So its albedo is quite high, close to 1 or 100%. So that is 80-90% is the albedo for freshly falling snow. So it will not be absorbing much energy. What if sun is fully radiating over there, even then it reflects back most of its energy. Only 10 to 15% of its energy is absorbed by the snow. So it means snow will remain over there at a similar same temperature, even if sunshine is there. As compared to a water body over there in the same environment, if a water body is there, its albedo is about less than 10%. So it will be absorbing 90% of the energy and it will be reflecting only 10% of the energy. So water will be heating up quickly as compared to the snow. So water evaporation will be more as compared to the snow. So albedo is one of the factors that describes the surface. That is simply the ratio of the energy reflected from a surface divided by the energy incident at the surface. So if we know the albedo, the vegetations, the greenery, so that has reflectivity close to 0.23, 0.25 is the reflectivity of the forests and vegetation. And the clouds have the reflectivity again of different value, whether they are at the lower level, at the higher level, whether they look dark or they look whitish. So their reflectivity is shown over here. The crops reflectivity is shown over here, 0.25 se leke 0.15. So reflectivity controls the amount of energy absorbed by the surface or a body of water, so that controls evaporation also. So going back to the slide, if any foreign material is available in the water body, for example, oil is mixed with the water, so then evaporation will change. If it's a vapor pressure above the surface of the that water body changes, if vapor pressure enhances and goes close to the saturation vapor pressure, evaporation will reduce. If vapor pressure is less above the surface and it is away from the saturation vapor pressure, means deficit is more. I think we studied this term vapor pressure deficit. That is the difference of the existing vapor pressure to the saturation vapor pressure. So if that deficit is more evaporation will occur. If that deficit is lesser. Another thing is albedo, that is a reflectivity of the surface. If something is very shining, mean it is very reflective or very whitish surface. So it is reflecting all the energy which is incident on that surface. So it will be absorbing less, so evaporation will be less. So these were the factors which we have gone through. So I take a break over here. If you have any questions, you are welcome. We have gone through the factors which affect the evaporation rate. 3 groups of factors have been discussed over here. Further, you should read the relevant part in the book Evaporation and its characteristics. कोई है question इसमें? No. So I take a break of 10 minutes. I stop recording. Stop sharing. And what I want to say that I am ending this meeting also. I will schedule next meeting with the help of the calendar so that nobody should be able to remove each other. So ये मैंने अभी meeting start की थी, तो ये calendar में schedule नहीं है. If we schedule a meeting in a calendar, then we can change its parameters. We can control who can remove other students. तो मैं इस meeting को end करके दोबारा आपको link भेजता हूँ. Okay. Thank you very much. Okay, welcome back after the break. So 23 students are left with me. And you might have noticed that university have asked all the teachers to add dean and chairman of the department into the group. Note किया आप लोगों ने? So now dean and chairman can join any class, online class. सारे खामोश हैं. Should we start the second part of the lecture? Anybody? कोई भी नहीं जवाब देता. मोहसिन राना ने हिम्मत की. हाँ मोहसिन बताओ, शुरू करें.
थोड़ा वेट कर ले, अभी काम में आ जाएंगे तो
अपनी फिक्र करो, तुम दूसरों की फिक्र जो नहीं आ रहे नहीं आ रहे. कंटिन्यू करते हैं. They will join us. Some are taking breakfast. Bad network quality. So in this part of the lecture, we will be explaining you a different terminology which we use in case of evaporation, and the second thing, different instruments which are used for measurement of evaporation rate. Two terminologies are frequently you would be able to distinguish between them. One is we call as potential evaporation rate, and another is one we call as reference graph evaporation rate. Potential evaporation rate and reference graph evaporation rate, and both are represented with the symbol capital E with a different subscript P we use for the potential evaporation, and subscript naught or 0 we use for reference graph evaporation, or sometimes we use E subscript R also, reference graph evaporation. There is another evaporation rate of evaporation which we call as crop evapotranspiration or crop evaporation. So we represent it with the symbol E C, E subscript C. So potential evaporation is the rate of evaporation per unit of an area. So evaporation rates are for a unit area. because if for a certain area, I know the evaporation from a unit area, for the whole area, I can find it by multiplying with the area, I can find the volume which is being evaporated. So when we mention the evaporation over a unit area, then the units becomes depth of water unit, millimeter or inches of, and because evaporation is small, so usually we express it in millimeters or inches of evaporation over a unit area. And most of the time we don't mention that it is over a unit area. So we should understand that if evaporation is expressed in millimeter or in inches, it is from a unit area. So potential evaporation is the evaporated water rate per unit area per unit time, and usually this time is a day because rate of evaporation is small, so we measure it on a daily basis. The quantity of water evaporated per unit area per unit time from an idealized extensive free water surface. A big water surface is there, extensive, the border effects are very minimal in that case. So extensive free water surface, if it is there, so whatever is the rate of evaporation of that extensive free water surface body, so that is called as the potential evaporation. That is considered as the highest rate of evaporation possible in that area. Potential evaporation is let us say the upper limit of evaporation in a certain climatic condition, in a certain weather condition. This is the rate of evaporation. So if we have no shortage of water, we have extensive free water body, free water surface. So whatever is the rate of evaporation of that free water body, so that is called as potential evaporation rate, EP. Usually other bodies like crop and these things will have usually less than this evaporation. Less than this. So potential is the highest rate of evaporation, and it occurs when there is a free water surface available, and it is extensive free water, not a very small water surface. Extensive free water surface, vast land covered with the water, like big reservoir, like oceans. So reference evaporation rate is rate of evaporation from an idealized grass crop. Idealized grass crop. Maybe it is not a real grass, but it is an idealized grass crop. Which crop? Which has certain characteristics. So rate of evaporation from an idealized grass crop. So crop type is mentioned over here. It is a kind of grass. Grass usually don't have big height. Grass usually don't have trunks and these things, so it is a special kind of vegetation. And usually they cover the whole land. It is not like one tree planted and then soil is there. So grass usually cover the land surface. So it is an idealized grass crop with a height of 12 centimeter. 12 centimeter height grass with a reflectivity coefficient albedo of 0.23 or 23%, and which is covering, completely shading the ground. It means it is when there is a well-grown grass is there without any disease, and it is disease-free, and it don't have any shortage of water, then it will be covering the whole ground. Otherwise, patches will be there. Over here it is soil, over here it is grass. So it should be covering the whole ground, completely shading the ground, and it don't have any shortage of water. So with these idealized condition, if a grass is there and the rate of evaporation of that grass is called as reference crop evaporation. So this grass is called as a reference crop. Why are we calling it as a reference crop? Because other crops evaporation will be measured with reference to this idealized grass crop. The scientists who are working on the evaporation of the agriculture plants or crops or fields, So they say it is difficult to measure evaporation for each crop separately. Let us first measure the evaporation of a standard or a reference crop. And if we know the rate of evaporation of that crop, then other crops will be related with this one, whether the other crop has more evaporation than this or less evaporation than this. So because other crops are referred to this crop, so this idealized grass is called as reference crop. So rate of evaporation of a reference crop, which is an idealized grass crop with a height of 12 centimeter or about, this becomes 5 inches के करीब बन जाता है. A 5-inch high grass or 12 centimeter high grass covering the whole land, shading the whole land, and which has a reflectivity or albedo of 0.23, and which should not have any shortage of water. Whatever is the energy available, whatever evaporation want to exist, water shortage should not stop it. So it should not have any short of water. So a well-grown grass crop of so much height, of so much albedo, is considered as a reference crop, and the rate of evaporation for that reference crop is called as reference crop evaporation, E naught. And units for rate of evaporation is always depth per unit time, and usually it is depth per unit day. And in SI, we use millimeter per day units for the evaporation. So clear? The potential evaporation is the rate of evaporation from an extensive water body, and potential and reference crop evaporation, or sometimes we call it standard crop evaporation, and represented by E naught, is evaporation rate of a standard or a reference crop. And there is a definition of the reference crop. It has a height. It is a extensive gross crop with a height of 12 centimeter with albedo of 0.23, and which is covering the whole land and which don't have any shortage of water. And sometimes they mention it is a disease-free grass also. So उसकी जो evaporation होगी उसको reference crop evaporation कहते हैं. Measurement of rate of evaporation can be done in a different way, and people have developed analytical approaches. Mean through calculation they want to estimate the evaporation rate, and they have carried out certain estimation using evapometer or pan evaporation method also. This method, analytical method, through computation, what they do is they have estimated the rate of evaporation by 3 different ways. One, by the way of water budgeting, as we have done in the case of water budgeting, as in the case of water budget equation, we have informed you that a rate of the total change of storage will be equal to the inflows in a certain area minus outflows from that area. So that will be equal to the change of storage of water in that area. So if we have all other parameters available in that water budget equation and only evaporation is not known to us, then rate of evaporation can be estimated using water budget approach. Do you remember it? Water budget approaching. So for a certain area from where we want to estimate the rate of evaporation, for example, for the whole Pakistan, if we want to have the idea of how much is the evaporation rate, so people can budget the water coming to the Pakistan, water change of water within a certain time period in Pakistan. It can be a year, it can be a month. It cannot be done on hourly basis, so it can be done on a larger time scale basis. We cannot have the change of storage after every day because it is difficult to measure the change of storage in ground. It is difficult to measure in reservoir and in atmosphere. So change of storage, for example, over the year period. So inflow, and if the change of storage is known, it can be outflows can be estimated. So outflow can be taken as the evaporation from this area if we assume that the groundwater outflow and the groundwater inflow are equal to each other, something like that. So water budget approach can be used to estimate evaporation of a certain area. Similar concept can be used with respect to energy budget, like you have done the water budget. Similarly, energy budget and the mass is similar concept as a water budget approach. In water budget, we are measuring the volume of water. In the mass transfer, we measure the mass of water, means the kg of water or the grams of the water, to estimate the water inflow and the water outflow and the change of storage. So energy budget, again, it is on the similar concept as a water budget. For a certain area, they see how much is the energy coming to this area, how much is energy going out of this area, and how much is the change of energy in that area. So change of the storage of the energy, change and the total inflow of the energy into that area can be used to estimate how much is the energy going out of this area. So if they know, if they estimate how much is the energy going out of this area, so then out of that outgoing energy, a part of the energy which is reflected back through radiation, that is taken out of that, and the rest of the energy is going out of that area through evaporation. So, so total energy which is leaving a certain area, which is going out of a certain area, can be divided into different parts. For example, one is direct reflection, that is going out. Another is transfer of the energy through evaporation. Another way of energy outflow from a certain area is energy going into the ground. If we can measure the change of the temperature of the ground, so that energy can also be estimated. If we measure how much is the albedo or reflectivity, that energy can also be estimated. So the rest remains is the energy going out of this area through evaporation. So if they estimate the energy, so much watts per meter square is going out through evaporation, so that can be related to the mass of water, that can be related to the volume of water going out through evaporation. So these three analytical approach are used to estimate the evaporation. One is the water budget approach, in which we estimate it through volumetric units. One is mass transfer approach, in which we use the mass of water, kg, or what we call it, grams of water. Another is energy budgeting approach, in which we budget the inflow energy, outflow energy, change of energy in a certain area, and evaporation is measured. But these are analytical methods and are dependent upon a lot of parameters required for estimation of these things. A direct approach, which is used to estimate the energy, is using the pan evaporations. So scientists and hydrologists, meteorologists, they have established different shapes or different kinds of water pans, pans containing water inside it, and they place it in the area where they want to estimate the evaporation, and the daily change of water depth in that pan is measured, and that is said to be pan evaporation. So that is related to potential evaporation, that is related to standard evaporation through experiments. So pan is quite frequently used and most widely used method for estimation of the evaporation in a certain area. Pan evaporation, the rate of evaporation from the pan, it shows the effect of the atmospheric factors in that area. The meteorological factors like sunshine, like air temperature, like humidity, like wind speed, all these factor effect on the evaporation are experienced by this pan. So whatever is the evaporation given by this pan is taking care of the climatic condition of that area. The method, one of the pan is called as US Weather Bureau Class A pan evapometer. There are different kinds of pans available, different kind of experimentation have been done. Most commonly used is this standard pan, Class A pan, which is developed by US Weather Bureau. And it has a certain diameter, it has a certain depth, it has a certain special placing recommendation that it should be placed in the area in this way. So those need to be informed to you. it has a standard kind of material with which it is made. So all of this, if are made as per the recommendation by the US Weather Bureau, then we say that this is a standard Class A pan, a US Weather Bureau Class A pan. This is standardized pan. So most of the meteorological station have this pan available for measurement of the evaporation. Out of all the pan evapometer, this Class A pan is most widely used. Class A evaporation pan has a pan of diameter 120.7 centimeter. 120.7 centimeter. ये फुटों में कितना हो जाएगा? 2.54 पे डिवाइड करो तो 47.5 इंचेस 48 इंचेस जो है वो कितने होते हैं? 4 फुट के करीब. About 4 feet diameter pan. So Class A evaporation pan is 120.7 centimeter diameter and depth is 10 inches or 25 centimeter depth, and it is made of galvanized iron. Don't try to change the material. So use the same material as US Weather Bureau have recommended, and its thickness is usually 22 gauge. The thickness of the steel plates are usually measured with the gauges. If the gauge is small, like 21 gauge plate will be thicker than 22 gauge plate. So 22 gauge galvanized iron plates are used to make this evaporation pan. And galvanized is what? It is a technique of protecting the steel plates, galvanization. Usually we dip the steel plates or the instrument in a liquid of zinc or some other protecting material. So we dip it into that liquid protecting surface, and this process is called as the galvanization. So galvanized iron 22 gauge is the thickness is used for making this evaporation pan, whose diameter is 120.7 centimeter, which is equivalent to 4 feet, and has a depth of 25 centimeter or 10 inches. It should be, of course, it should be free from the leakage, and it is usually provided with these two things. One is called stilling well, a small dismiss. How is my voice quality now? चलेगा काम वेट करूं. If you're getting my voice or not. So let's continue with this mobile data. Already share screen. So we were talking about Class A pan and its construction or its characteristic depth. I was telling about the steel gauge. के अंदर एक cylindric kind of well is provided so that you can measure the depth with very precision within that stealing well. Outside stealing well, maybe if air is blowing, there are waves inside this pan. But manually, it is very calm, and you can measure it, the depth of water in the pan accurately with the help of hook gauge. So if I show you, this is the pan over here, and there's a stealing well, a cylinder which is open from top. So that is available, and that is suspended within this pan. And if we want to measure the depth of water in the pan, we measure it in the stealing well, because it is open at bottom, open at top. So whatever will be the water level in this pan, same will be in the stealing well. Just to avoid the ripples or just to avoid the waves effect on the water depth. This one is over here. So then here is steering well, and this instrument, this part is hook gauge. It has a hook kind of arrangement at the bottom and inside, and we touch the tip of the hook, we bring it to the level of water inside this pan, and we measure the. And you see its standard placing arrangement. There is a wooden platform underneath it that is standard, and its height is also standard. It should be about 150 millimeter or 15 centimeter above the ground. So about 6 inches above the ground it should be. So if it is placed on concrete platform, that is not standard. If it is placed on soil, it is not standard. So it should have an air circulation around this fan, and that air circulation is assured with the help of this wooden platform which has opening inside it, and it allows air to circulate around it, and it avoids the pan in contact with the soil, which can have higher temperature or lower temperature. So it is like it is placed in the atmosphere, not in contact with the ground, because wood is not a good conductor of heat. So you should remember these things: its size, its shape. It is not filled to its brim. It's total 25 centimeter, but it's usually up to 20 centimeter of the depth. When is filled with a clean water, 20 centimeter of the depth. It is placed on the wooden open frame that I have already informed to you. Daily evaporation is measured using this. At the fixed time, the gauge reader will go over there. Will note the reading with the help of the hook gauge in the stilling well, and he will note it down. And then he will fill the pan back to the, for example, he wants to maintain a 20 centimeter depth inside. So he will fill whatever water has been evaporated, he will put that water inside it, and it will be reset. So next day when he will go to the pan evapometer, he will note the reading of the reduction of the water in that pan, and that will be noted as the evaporation for the previous day. That will be noted as the evaporation for the previous day. If rainfall occurred, because this pan is open from the top, if rainfall occurred, that will also go into the pan. So that will cause error in the reading of the evaporation. So sometimes yesterday, if the depth was depth of water was 20 centimeter, and today you went to the pan and you have seen that 21 centimeter is the depth, means more water is there, means there was the rainfall over there. So for that purpose, whatever the reading you have taken from the pan evapometer, that evaporation reading you have taken from the pan evapometer, subtract the rainfall of the previous day out of that. If you usually these pan evapometer are installed at the metrological station, and the metrological station usually have rain gauges also installed over there. So from the rain gauge reading, subtract that rain depth out of this evapometer reading. Then note the net evaporation for the previous day. So that should be taken into account by the gauge reader. Adjustments are made to the evaporation values if rainfall occurs during a period of measurement. So after measuring the drop in water level, after measuring the reduction of water level in the pan evapometer, water is added to the pan to bring the water level back to the original position. So that is the method of measurement of evaporation rate on daily basis using pan evapometer of any kind. So class A pan evapometer has a standard kind of, has a specific diameter, has a specific depth, and have a specific kind of environment in which it is placed, surrounding environment in which it is placed. So that should be kept in mind. Sometimes one cause of error from this pan, some birds can take water out of this. They can drink, they can come over here and they can drink water out of here. To avoid that kind of interruption from the birds or by the animals, bird may not take much water, but if some animal reach over there, cow or buffalo, they can take a lot of water out of it. So that can be protected with the help of some protection around the metrological station, some screens or some kind of what we call it, walls need to be built over there around. So trespassing should be avoided. And another protection can be done at the top of this pan with the help of the screen. So that can avoid the reach of birds over here, and no loss of water will occur over here. But this can reduce, this screen installed on the pan evapometer can reduce the rate of radiation reaching to the water, which will affect the evaporation reading. So don't try to match a pan without screen and pan with screen reading with each other. They will be a little bit different from each other. So if you want to compare, you should compare two pans with screen or two pans without screen with each other. You see on this actual installation, it is placed on the wooden framework. It is placed with the screen over it, and it has an opening so that the sealing well can be used to measure the depth of water inside it. It has to measure the local condition of wind speed. It has an anemometer installed with it, and somewhere rain gauge will also be installed in the neighborhood also. So screens, pan with the screen are available, pans without screen are available. If you have a evaporation reading from the pan, so it can be converted into different kind of evaporation. For example, evaporation from the lake or the reservoir evaporation can be estimated by multiplying with the pan coefficient with the pan evaporation reading. Over here, EP is represented by pan evaporation. Previously, we said EP is potential evaporation. So you should take into account. So at different places, different symbols can be used. Over here, they have explained that EP is representing pan evaporation. And of course, this is not equivalent to potential evaporation. So if EP is representing the evaporation measured using the pan, and if we multiply coefficient, it can be converted into the reservoir or lake evaporation, EL. So usually the pan manufacturer through experiments, he gives us the pan coefficient, and usually the class A pan has a coefficient of 0.7. Class A pan without screen has a coefficient of 0.7 to convert the pan value into the reservoir evaporation. So that is ratio of actual annual lake evaporation divided by the pan evaporation. It is the ratio of these two. So if Kp is known, that is the pan coefficient is known for a certain pan, we can convert the pan value into a lake or reservoir evaporation. Other kind of settings of these pans and other kind of pans are possible. Some pans are sunken into the ground. They are ground or the soil is deep, and we place it under the ground, and the top of the evapometer is flush with the ground at the same level with the ground. Sometimes it is floating. Sometimes it is floating like it is shown over here within the reservoir to mimic or to copy the similar condition as the reservoir is experiencing. The pan is also placed in the similar condition. So floating pans are also used by some of the organizations. I've shown you earlier a pan placed on the wooden surface or some other surface. So pan can be sunken, pan can be floating, can be surface. Most of the time we are using surface pan evapometer for measurement of. So this is a kind of sunken pan. A part of the pan is, so it is not flush with, it is a little bit higher. So part of the pan is sunk into the soil. So this kind of setting is used by those people who are interested more in estimating the evaporation from the vegetation which are grown in the soil. So vegetation the pan, because the surrounding of this pan is having the similar temperature or similar environment as this vegetation is experiencing. So they say that putting it on a platform, putting it on a higher ground at the surface is not a good representation of the surrounding environment. If we place it, they put it a little bit higher so that water should not into the pan from the surrounding surface. So they collect, because their elevation from the ground is higher, so they have some problem also. They can collect some trash moving around into it. They are difficult to install and clean and repair. The pan which is placed on a higher ground, that is easy to clean. We can drain, but draining it out is a little bit difficult. We have to use the buckets or some pumping arrangement to drain water out to clean it. After a certain time period, we need to clean the pans so that any dust, any soil particles should be removed out of it. Leaks are difficult to be detected out of the sunken pans. So this is one kind of arrangement. So please go through it. And these sunken pans can be available in different sizes. And 3 different sizes which have been experienced by different people placed over here. Young pan has a dia of 2 feet. Bale of Plant Industry BPI has a dia of 6 feet. The standard pan, remember, that has a dia of 4 feet. And Colorado University, Colorado pan have a diameter of 3 feet. So they have different diameter and depth, and that can be used. Floating pan is used by those people who want similar environment as that of the reservoir, and it is difficult to operate. Reaching over there and measuring is difficult. But people for research, they can use such kind of pan also. Surface are most used. I have already explained it to you, and here is the hook gauge shown to you. The hook gauge is used to measure. Another thing, in addition to the evaporation, is transpiration, which is the evaporation from the stomata of the plants. So if the evaporation occurs through the plant leaves, then we say this evaporation is transpiration. Then we say this is a transpiration. So evaporation of water through the plants is called transpiration, and it occurs chiefly at the leaves of the plant when they open up their stomata of oxygen and carbon dioxide, and it is also a huge amount. For example, for 1 acre of maize crop can transpire about 4,000 gallons of water throughout its crop period, throughout its growing period, 3-4 months growing period. It can transpire about 4,000 gallons of water out of the 1 acre of the maize, and that is equivalent to a depth of 30 more than a feet of water transpires throughout the crop in 1 acre land. That's it. And these are also affected by the similar parameters as the evaporation is affected. In addition to that, a crop characteristics, a type of the crop also controls the transpiration. So this concludes our today's lecture of evaporation and how it is measured. So if you have questions, you are welcome. If you can answer all, evaporation and transpiration are important factors of metrology or hydrological measurements. So if no question, I stop it over here. I stop the recording. And I stop the sharing. So these slides are already given to you. I am putting the slides for the next lecture. That is the gauge measurement, river gauging. So that I put on the WhatsApp group. Please store them. Recording is being saved. Yeah. Start recording. Okay, thank you very much. I am ending this class.